The F180 Robocup League, hosted annually, pits teams from all around the world against each other with the aim of building robots capable of playing and beating a professional soccer team by 2050. This semester, Team 28 was tasked with building a soccer bot that would be able to compete in a modified version of the F180 League. This required the team's robot to be able to play on a 2x2 meter field, with a green felt surface and a blue and yellow goal on each side. The constructed robot was required to be no more than 22.5 centimeters tall and 18 centimeters wide, and to be primarily black in color. The robot was made up of 4 primary systems. These were the drive system, the kicker-dribbler system, the vision system, and the AI navigation system.
The drive system uses a differential system consisting of 2 low-power, 6-volt, 101 metal gear motors with plastic wheels attached. A plastic caster wheel is also used to help with the stability of the robot. A L293D motor driver IC is used in conjunction with the 2 individual motors and is wired up to the GPIO pins of the Raspberry Pi. Simple Python functions with PWM signal controls allows the Pi to set the outputs of the pins to the IC to move each individual motor in a set direction at a set speed. This provides the robot with a range of movements which will help navigate towards the ball and designated goal, while also avoiding obstacles on the field when integrated with other subsystems.
The AI system was responsible for navigating the robot within the field. Navigation methods such as simple Bratenberg, vector field histograms, and global mapping techniques were considered. Due to the nature of the task, it was deemed that potential field navigation is the most suitable. In the preliminary stages, VREP simulations were used to test navigation code performance before the physical robot was built. Due to time constrictions, the final navigation system consisted of a reactive state machine, which would tell the robot to perform different actions based on its state. The robot would do this using the range and bearing of objects provided by the vision system. Depending on its state, the robot would either be locating and driving to the ball, or one of the 2 goals, avoiding obstacles, or kicking the ball. Overall, the system performed soundly on demo day. However, it was found that the robot would prioritize avoiding obstacles very far away from it over seeking the ball. Given additional time, this would be remedied by implementing a range within which the obstacle avoidance algorithm would activate.
The vision system was designed to detect the ball, obstacles, goals, and walls and output their distance and bearing to navigation. Different color spaces for thresholding were considered, such as RGB, HSV, and lab. However, HSV was used. Using image processing techniques, the video feed from the Raspberry Pi camera was blurred and converted to an HSV image. Further processing included shape detection, such as contours for roundness, accompanied by a range of radiuses for the ball to limit the distance the ball can be seen and reduce false positives. Distance calculations were done by comparing the object's real size with the perceived one and outputted in centimeters. The bearing was measured to the center of an object and ranged from -30 to +30 degrees. Due to time restrictions, the final vision system only thresholded for the walls. However, given more time, the robot would be able to avoid walls.
The kicker-dribbler system consists of a solenoid and tapered rubber bar. The kicker was required to kick the ball at a velocity of 2.5 meters per second, whereas the dribbler needed to acquire the ball and keep the possession of the ball while the robot is moving. When choosing a kicker and dribbler, the following must be considered: affordability within the budget, mechanical complexity, electrical complexity, and integration within the system. We had the options of rack and pinion, spring, and pneumatic kicker designs. A solenoid was selected because of its mechanical and electrical simplicity, along with the ease of integration. However, the cost of a solenoid comes at a higher expense than other systems. The dribbler consisted of a simple 3D printed bar that tapers to the middle. Rubber has been added to provide grip to the ball. In the final product, basic code was written to switch a transistor on and off to complete the circuit to the solenoid and provide a kick. The voltage was boosted using a DC to DC converter and stored in a capacitor. As shown, the kicker was able to kick the ball, but not as fast as required for the project. The kicker system wasn't able to be fully implemented into the final demonstration. The dribbler was able to hold the ball while the robot was in motion. A problem we encountered was that the dribbler drained a lot of battery due to being constantly on. If given more time, a larger power bank for the solenoid could have been used to provide a higher voltage, meaning a faster kick and full integration into the final demonstration. More time would also mean we could implement a function where the dribbler can turn on and off when necessary.
The robot Team 28 built may not have been perfect, however, it managed to fulfill a significant portion of the criteria reliably and was able to demonstrate this on demo day. Thank you for watching Team 28's video. We hope you enjoyed it.